The first myth was a prevalent belief for many decades, but has been soundly disproven by research. Myth number one, students learn at different rates, so they will catch up later. While it's true that not all students are alike and there are variations in learning rates, what is perhaps more true or more important to understand is that students who fall behind are likely to stay behind, and if they're not provided support. The earlier the support to catch up, the better. The further behind a student is, the more intensive the support needs to be. Benchmarks for reading and math are set at levels that all students, except possibly those with learning disabilities, can and should attain. There's ample research to back this up, such as studies from ACT, Gary Hord Nugent, Bailey, Shaywitz, and others. And keep in mind, kindergarten and first grade are not too early to identify and address learning deficits. Because identifying and addressing learning needs at all grade levels is important, I want to briefly call attention to practices of multi-tiered systems of support and response to intervention. According to McIntosh and Goodman, MTSS is a coherent, strategically combined system meant to address multiple domains or content areas in education. MTSS is important as a systems focus within a district or school on meeting the academic and behavioral needs of all students. I'm not going to delve deeply into MTSS since that's not the focus of this webinar. However, it's good to recognize that what we're talking about in this webinar is part of MTSS and RTI. It's worth just taking a moment to review key components of RTI because these heavily impact the success of math support for struggling math students or math interventions. Leadership and a team that plans, monitors, and drives an intervention system are critical for school-wide and district-wide success. One of my colleagues at CORE was just telling me about 2 different schools she was working with and how the leadership at one school was focused and drove an emphasis on supporting struggling learners in both math and reading, versus another school in the same district with leadership that at most provided suggestions to staff on interventions. The results have been very clear. The school with the focused support on addressing learning gaps is far outperforming the school that was driven by suggestions for interventions. Additionally, research has proven that schools that succeed with RTI have leadership RTI teams that monitor and manage intervention systems within the school and use data to drive decision-making with generally 3 tiers of instructional support. Those 3 tiers of instructional support include Tier 1, which is the core instruction itself, which can include some differentiated support within the core instruction to address immediate or emerging gaps and misconceptions. Tier 2, which is small group instruction, is instruction designed to address more persistent gaps, very weak or missing important prior knowledge, or continued and deepening struggles with understanding core instruction. Tier 2 can take place within core classrooms, or it can be additional time in a support class. Tier 3 addresses severe learning needs, typically students who are 2 or more years behind in key areas of mathematical understandings or skills. Tier 3 requires working with students outside the core instruction, and in extreme cases may even replace the core instruction with what is called an intervention core class. My final words on RTI itself are to mention the 4 main steps in the RTI process. The MTS RTI team first explores and identifies the school-wide needs, resources, and personnel that are likely to be part of the system for academic support. Then a plan is put together for how to identify and place students, along with what assessment systems and data will be collected, how it will be used. The plan includes what interventions to be put in place, what content will be taught, who will the teachers be, and how students and programs will be assessed. Additionally, the plan includes how interventions will be implemented, such as you might just do 1 or 2 classes to start with and then expand from there, or the whole school will implement it incrementally. And then the plan is implemented. And finally, interventions must be sustained with ongoing support and be monitored. Part of sustaining a system is to continually monitor its effectiveness. We want to know where the interventions are where they're working and where they're not working, so we can see how to improve them. We should monitor if students are closing gaps and if they are able to progress out of the interventions, or if at best students are just treading water and not actually catching up to grade level proficiency. Those important components of an RTI process bring us to the key areas I'm going to address throughout the rest of this webinar as they relate to providing support for struggling students in math. I'll talk about who are the students that need and will receive added support. How do we decide on what to teach? What is the content focus for added support or intervention? When to teach? Where's the time in the schedule for providing added support? How to teach? What are the basic instructional techniques to use for different levels of support? Who are the teachers that will provide the added support? When should we use a publisher intervention curriculum program? When that should be used versus other resources? What are the best intervention materials to use in different situations? And why we need to assess, review, and revise intervention programs. Now next, let's look at effective teaching techniques and how these are similar to and different from the techniques that may be used for core instruction. One common complaint from teachers is that students come into their math classes unprepared because students don't know their math facts and are not fluent with basic procedures. This often leads to a common refrain we hear, and this leads to our myth number 7. Students just need lots and lots of practice with math facts. Well, of course it is true. Students do need plenty of practice, both immediate and distributed. This is even more true for students struggling in math. As we've seen in intervention, what we have them practice on is a subset of earlier math concepts, the key concepts that are most meaningful for helping these students move forward. However, it is just as important to recognize that students rarely need extra support simply because they don't have all their math facts memorized. As described in research and by math experts, these students still need understanding of concepts, fluency with the math, and ability to apply the math. The key difference is in how we narrow that focus on specific concepts for these students. Additionally, with more focus for struggling students, we need to make math connections very explicit. Take a moment here to read this statement from Marilyn Burns.
Students who need intervention instruction typically fail to look for relationships or make connections among mathematical ideas on their own. They need help building new learning on what they already know.
Thanks again, Emily, for reading that. So it's important for students to see connections between and within mathematical ideas. Conceptual understanding is the foundation for fact and procedural fluency, just as fluency is part of a foundation for continued learning in math ideas. However, students in intervention struggle to see those connections on their own or on their first pass through a concept. Therefore, we as teachers need to provide more explicit direct instruction that attends to these connections. We still need to require students to think and reason about math and make some connections, but as teachers, we'll do more of that heavy lifting than we typically do with a Tier 1 instruction. For example, suppose students are making a common error when adding fractions with unlike denominators such as 1/2 plus 1/4. They incorrectly add the numerators and the denominators to get the wrong answer of 2/6 rather than 3/4. To address this misconception about adding fractions, rather than simply reviewing the correct procedure again and again, which students in intervention will have likely seen multiple times already, a better approach is to return to the conceptual level and the important math concepts this is built on. Use the number line to start with to visually show adding 1/4 and 1/2. Provide a number line such as this that's shown on the slides and have students label the parts on the number line. Then have students justify the placement of 1/4 and 1/3 and 1/2. Make this clear for all the students where those go and why they go where they go. Then provide bars to visualize the size of the fractions on the number line. Show students how to make the drawing on their own number lines that illustrate 1/4 plus 1/2, then have them determine the value of these two bars when they're put together, where they end up on the number line. Have students locate their answer of 2/6 on the number line and compare this to the visual of 3/4. And we do that because this helps convince students that their answer maybe it really is wrong, because they see that the answer should be 3/4. And this provides a nice visual proof for that. Misconceptions can be like weeds. They're very hard to get rid of. So you really have to take the extra step to help students see that, oh, that answer was wrong. It's not just because I have a procedure that gets a different answer. It's because it really doesn't look right. I mean, there's a reason for it. So we want to convince students about that. And next, remind students about adding whole numbers and how fractions are like adding whole numbers, that we add like units together. We add the ones to the ones, the tens to the tens, the hundreds to the hundreds. And then we explain that 1/4 and 1/2 are not like units. They're not ones and ones and hundreds. And because they have different denominators, you have to make them like first. So in order to add them together, you have to get them to be the same unit just like we do with whole numbers. So first we change one or both fractions so they have the same denominator, because the denominator is the unit of the fraction. Now we move to the procedure for adding the fractions. We change 1/2 to 2/4, and then we add 1/4 and 2/4 and get 3/4. Have students identify this on the number line and compare it to the visual model. This kind of explicit instruction, combined with student interactions around the connections within the math, allows students to see why a common error is wrong and why the correct procedure makes sense. Next, we would model and provide guided practice on a couple more like problems, and then have students practice this skill. Practice should include having students illustrate on number lines a couple of problems on their own to solidify the connections between the procedure and the concepts in their minds. Then students can practice the procedures many times to build fluency with it. So you see from this, we include some student thinking and reasoning into the sequence of instruction by doing things like we provide a number line without numbers and have students fill those in. Have students think about where those numbers are and have them justify the placement of the numbers 1/4 and 1/2 and 1/3 on the number line. And we ask them to figure out where the 2/6 goes on the number line and compare that to the answer of 3/4. And we have students make a drawing of their own of these. Let them see and make that illustration to show what the value of the fractions are and what they are when they're put together. So we can be very explicit about the math. We can scaffold the problem to give access to all students and ask targeted questions within this framework that ask students to do some thinking that lays the foundation for the mathematical connections, the math connections that are going to be made clear, most likely by us. By connecting visual models to math ideas, we help students see and understand concepts and see the sense in those given procedures. Connecting to prior knowledge, such as connecting fractions operations to whole numbers, also reinforces the consistent and connected nature of mathematics.